Hi. For the first week in discrete math here, what I want to do is focus on what kinds of things discrete math is, what kind of thing discrete math is. I could give you a definition, and I may do that later, but I want to start instead by giving you several problems which are typical of discrete math. And so the very first video here, beyond the introduction explaining why we're online at all, is going to be about a particular discrete math problem. So this is called the candy problem. Let me describe it. It's in a Google Doc that I sent you through Canvas messaging. I sent you two. The first one was a mistake. It was an actual Word document. I want to use the Google Doc. It'll make things a little easier. So use the second link I sent you. I've actually deleted the first file. All right, and so here it is, the candy problem. 4 men sit at a round table. Each has a certain number of pieces of candy in his possession. Possibly everybody has a different number. There's also an unlimited number of pieces of candy in a pile in the center of the table. The action proceeds in 3 phases which alternate forever. The evening up phase, everybody who has an odd number of pieces of candy takes one more from the center of the table. So then everybody will have an even number of pieces of candy. The division phase, every man divides his pile in half. And then the passing phase, every man passes half his candy to the person on the left. And they keep doing this over and over and over again. They go back then to phase 1, even up again, divide again, pass again, even up again, divide again, pass again. The question is what eventually happens. Let me give you, I've made a little diagram of this. Let me show it to you how it works. This is just a way to picture it. Here's our 4 men, A, B, C, and D. Let's suppose that A starts with 5 pieces of candy, B with 3, C with 4, and D with 6. So the first phase is the evening up phase. It means everybody who has an odd number of pieces of candy gets one more to make it even. So A only has 5, A gets another one to make it 6, B only has 3, B gets another one to make it 4, C and D already have an even number, so nothing changes for them. Once everybody has an even number of pieces of candy, now they can divide their candy in half. So A's 6 pieces get divided into 3 each, B has 2 each, C has 2 groups of 2 each, and D has 2 groups of 3 each. And now they get to pass to the left. So everybody takes one of their halves and passes it to the person on the left. If you look at what that does, it means that everybody's number of pieces of candy might change. A passes away 3 and gets 3, so his doesn't change. He keeps 6. But B passes away 2 and gets 3, so he will now have 5. When they're all done, it'll look like this. A will have 6 now, B will have 5, C will have 4, and D will have 5. And now we continue. Once again, the odd-numbered ones get an extra piece of candy, and then they divide them in half, and then they pass again, and so on and so on and so on. That's as far as my diagram goes. All right. So my question is, what happens eventually? Now, you might complain that that's a really ambiguous question, but it's because I want you to figure out what happens eventually. I don't want to tell you what it might be. Does the number of one thing that could happen is every time somebody has an odd number of pieces of candy, they get one from the middle of the table. So it could be that the number of pieces of candy in the game increases without bound, that it basically can grow to infinity if you have the right series of numbers. So that's one question to ask. Another question you can ask is, does the number of pieces of candy in play ever decrease? And I think you can see pretty obviously that that's not true. It can never decrease. That can never happen. It can never decrease because nowhere in the game, in any of the phases, does anybody lose any pieces of candy in play overall. I mean, they lose somebody's pieces of candy may decrease for them, but only because they passed it on to the person to their left. So the number of pieces of candy certainly doesn't ever decrease. Does it ever stop growing? Do you ever reach a place where everybody always has even numbers only? As long as they keep passing, it just always stays even. Do you ever reach a place where nothing changes? Where whatever situation you have, just all the piles stay the same, or that they rotate in a loop so that you get the same patterns over and over again? Those are questions I want you to ask. Now, I'm asking you to come up with the best solution you can collaboratively as a group by Friday, and then I'll respond to it next week a little bit on Monday and tell you what the solution is. But there's a couple things to keep in mind here. There's sort of 2 different ways you can investigate this, and they're both an important part of mathematical reasoning. The first thing you need to do is just try to make some good guesses. I don't mean random guesses, I mean intelligent guesses. So you might want to look for some patterns. Try this out with different number of pieces of candy. What if they all start with 1? What if they all start with 10? What if they all start with 5, 6, 7, and 8? I mean, what are the different results? If you want to, and this might be a really good idea, you might want to write a program to do this problem and just put in numbers and see what you get. So there's a lot of things you can do here. if you do, so whatever you put there, put it in the Google Doc. If you come up with, if you say, I tried it several times and this kept happening, put it in the Google Doc. If you say, I wrote a program and this is what it gave me, put it in the Google Doc, or maybe even post the program to the Canvas page somehow. Email it to everybody, or I can't remember if I have a forum set up, put it there, or something like that. Or share it as a Google Doc, except it'd be a CPP file. Whatever you'd like to do. The second thing, though, is I don't just want guesses about what happens, even if you're pretty sure about what happens, because that's not mathematically complete. Mathematically, you don't want to just say, this is what usually seems to happen every time I try it. Even if you run a program, you don't want to say, this is what happens the first 1,000 times I tried it. What you want to say is, I'm sure that this happens and I can prove it. So how do you prove it? Well, in this case, that doesn't mean any kind of formal 2-column proof or anything. It simply means give me the reason why you know it happens. Explain why it has to be that way. For example, I didn't do it formally, but I hope I just proved to you a minute ago that the number of pieces in play in the game never decreases. And the reason it never decreases is because nothing they do ever decreases the number of pieces of candy. The evening up phase always just adds candy. The division phase doesn't change the number of pieces of candy. And in the passing phase, it also doesn't change the number of pieces of candy overall. And since that's all they do, the candy never decreases, and therefore it has to either increase or stay the same. So that's kind of a little miniature proof that the number of pieces of candy from moment to moment in the game or in the situation never goes down. So that's the kind of thing you can give me as proofs. Give me reasons why things have to happen. All right. The way this is going to be graded, officially, right now on the Canvas page, it doesn't show anything about this at all. It just simply says that your first homework is due in about 3 weeks. Your first test is due in about 3 weeks. So I've set those up so they're not due until after we meet together. But I am going to, I am going to require this as an additional assignment. I may add it to the Canvas page. I may just leave this to be your assigning of it, your notice that it's assigned. What I want you to do is give me the best answer you can collaboratively by the end of Friday. Now, you can get full credit for this even if you don't get a complete answer. It depends on how much you've done and what you've shown me and whether I think you've done a good job of exploring and sort of seeing what's going on. I can tell who's written what and see what the editing has been and so on like that. So I'll grade this individually, even though you're sort of doing it collaboratively. I'll look and see what work you did and sort of give you credit for that. So that's the idea. I'll probably, I haven't figured out yet, I'll probably grade this fairly easily and then just add it as some sort of a factored in somehow to the grade for the first homework. Okay, one other thing I want you to do before the end of this week, and that is to read Chapter 1. Chapter 1, it doesn't have anything I'm going to directly test over, but it does the same kind of thing as I did here with the candy problem. It covers several different typical discrete math problems, very different from this one and very different from each other, but they're all very similar in that they have a discrete math feel. You'll see a whole bunch of them mentioned, but the three in particular are in section 1.2, I think is the PERT diagram problem, or it relates to PERT diagrams. In 1.3 and 1.4, I forget which is which. One of them is the knapsack problem, which is a very famous open discrete math problem, and one of them is the matching problem, which is a famous problem which has pretty much been solved. We're going to talk about the matching problem actually for a whole week later on in the semester, probably. But look at those. As they go through, though, if we're sort of the same idea as this is, it's just to give you a feel for how discrete math looks. They'll also do a couple of other things in Chapter 1. As they talk about these problems, they bring up some of the other areas of discrete math that we're going to look at. They talk about graph theory. They talk about combinatorics. They talk about set theory a little bit. So we're going to be covering those things as well. And so it's just a good introduction. But you don't have to do anything with any of that. Just be thinking about it. I'm going to do one more video this week, which will be related to this week, which will be to look at 3 other problems which are all part of the first homework. And it's sort of like the candy problem, but they're their own. And I'll at that point tell you more about how the homework works. It's a little bit funny the way I'm grading it, and a little bit more how the tests work. And then next week and the week after, we're moving into looking at logic, which is actually at the back of the book in Appendix 1 and 2, A1 and A2, and a little bit of set theory, which is the beginning of Chapter 2. Most of you probably know some logic and set theory, and so it may seem fairly simple, but later on we'll get stuff you probably haven't seen, and it'll get more complicated. So that's what's going on. So by Friday, hopefully you guys have something for me here, and then I'll respond to it a little bit in video form next week, and we'll see where it goes from there. Thank you.